So in this video lecture, I'd like to go through the topic of FET transistors. So FET stands for field effect transistor, and the main difference from the BJT transistor that we've covered from the previous lectures is that FET transistors are voltage controlled, whereas the BJT transistors are current controlled. Also, FET transistors tend to have higher impedance. So there are quite a few configurations of FET transistors, but we will focus on the main two, which are GFET and MOSFET. I will just call it MOSFET. So these transistors are used in many cases, for example, switches, amplifiers, even sensors. So it's good to know this kind of configurations. So the first type is the GFET transistor, and the GFET transistor is made out of a graphene. So the channel of a transistor is made out of graphene. As you can see on these pictures that I've taken from the same book I cite all the time, it's a book, Introduction to Circuit Theory, and I really recommend this book. So there are two types of GFET transistors. These are N-channel and P-channel. You can see the N-channel transistor here, whereas the lower one is the P-channel one. They are quite similar. The only difference is their direction of current. And of course, the depletion and N channels are switched. Keep in mind that what is flowing through the N channel is electron. So electrons flow from source to drain, but conventionally we say that it flows from drain to source. Whereas in P channel, we say that there is a whole flow, but mathematically we take it as positively charged particles. So they flow from source to drain, both conventionally and just mathematically, okay? So here we see a very important illustration of what usually happens. For example, let's say you're supplying some voltage VDS, right? And it doesn't necessarily have to be higher than VGS. However, as VDS grows, the depletion region will become bigger and bigger. As a result, it will end up narrowing down the N channel and creating a pinch-off. Please do not assume that there is no flow. There is still flow of electrons. However, it will be obstructed and result in saturated current. So why this happens? It usually happens because as VDS grows, the gate to drain bias will be more, let's say, reversed, and as a result, the depletion region grows. The same thing happens with the P channel, but it's just opposite polarity. So this is usually how they illustrate the N channel and P channel GFET transistors. So as you can see, the current direction is different, but the remaining things are almost the same. So current direction is just a sign convention, okay? There's not much of a drastic difference. So we usually approximate IG is equal to 0, and thus the ID will be equal to IS. Also, there is a really interesting equation which is called the Shockley's equation, which states that the current ID will be equal to the maximum, let's say, drain current, IDSS, multiplied by 1 minus VGS over VP, which is the cutoff voltage, squared. Please keep in mind that the shockless equation you're seeing over here is applicable only in simplified circuit analysis problems, whereas in real life it's not quite true. So we can use this equation and say that GFET is almost like a depletion MOSFET, but it's rather a modeling convenience rather than a physical law, okay? Okay, so there's also a second type that we will cover today, and it's called MOSFET. So there are two types of MOSFET transistors. The first one is enhancement, and the second one is depletion. So the difference from GFET is that the channel is made out of silicone. However, the insulating material is similar for both of them. There is no material that is used all the time, but usually they use silicone as well. So the difference between enhancement and depletion is that depletion already has a conducting channel. So by that I mean a channel is just a thin layer that surrounds your material, for example, the silicon in this case, and current can go through it. In case of a depletion MOSFET, there is already a channel, but in case of an enhancement one, there is no channel and it is created throughout the process. Whereas in a depletion one, it is rather reduced in size by applying, let's say, a gate voltage of a proper polarity, okay? So these two representations, let's say 4 representations, is what you will usually see in circuit analysis. So the left column is the N-channel depletion MOSFET, whereas the right column is the P-channel depletion MOSFET. Also, please note that this particular figure is specific to depletion type of MOSFET, not the enhancement one, okay? Sorry for the misunderstanding. Also, what is interesting about the depletion type of a MOSFET is that in simplified circuit analysis, from a mathematical point of view, they are pretty similar to GFETs, and the Shockley equation can be used as well. Also, the Ig is equal to 0 as well as Id is equal to Is is true too. However, please note that the physics, the underlying physics, is different. When it comes to enhancement type of MOSFETs, it's different from the depletion type in a sense, as I mentioned before, is that the channel is created throughout the process. And for this particular type, we say that when current VTS grows, the voltage grows, the current that flows through the D grows as well. But when it's constant, the current D will be equal to IDSS, okay? So these are the configurations that you'll usually see in circuit analysis. The left one is the N-channel enhancement MOSFET, and the right one is the P-channel enhancement MOSFET. As you can see, they're pretty similar. The only difference is their sign convention.